Hi, in this video we're going to be talking about what happens when you take an n-by-n matrix and either add up all of its eigenvalues or multiply all the eigenvalues together. So to start out with, we have the definition of a trace of an n-by-n matrix. It's denoted TR of A, and it's the sum of all of the entries on the main diagonal. Okay? This theorem here says that if you take the sum of all of the eigenvalues of A, you get exactly the trace. Before we get to the proof of this, I just want to point out that if A is a triangular matrix, then its diagonal entries will already be exactly the eigenvalues of A. So adding up the eigenvalues and adding up the diagonal entries are exactly the same thing. So this theorem should be obviously true for the specific case when A is a triangular matrix. But it turns out that it's true in more generality. Now our proof here of this theorem is going to rely a bit on some facts about determinants. So let's try to walk through them in a clear manner. So when you take the determinant of an n-by-n matrix, what you're going to get is the sum of a bunch of products of these bij's. Okay? So I've written that as the sum of a bunch of these products. Each of these products will also have a sign that's associated to them. So you might be adding some and you might be subtracting others. And this product, together with the sign, is the thing I'm going to call a term. So when I refer to a term, that's what I mean. So this sum here has n factorial different terms that we're adding up. And in each of those terms, we have a bunch of bij's, and each I appears exactly once in the term, and each j appears exactly once in the term, where the I and the j values are ranging between 1 and n. So each of the i's and j's appear exactly in one of the factors bij of the term. Okay? We can take a term and order the factors. So we can always rearrange the factors because multiplication is commutative. And we're going to order them by their first index. In other words, by the row that they came from. Okay? So we're going to put the first row's factor here, the second row's factor here, and down to the nth row's factor. Okay? The column that these things came from is just going to depend on which factor we're looking at, or which term that we're looking at. Okay? And I've ignored the plus or minus sign out here, so this isn't quite the entire term, but it would be if there was a plus or minus sign. So let's try to see what we can say about the plus or minus sign there. So I've ordered these factors by the row number, and then we have a list of j's. And I've written these j's with an index, so this is a double index. So it's bi, and then the second index, the column number, I'm calling ji. So the first one is j1, j2, all the way up through jn. Now this is a list of all n columns. We don't know what order they're in, but it's a list of the numbers 1 through n, and it's been rearranged. So we call that thing a permutation of these numbers 1 through n. Okay, we're now going to define this set S, which looks a little bit funny, but it turns out it's a really natural thing to do. It's going to be the set of pairs of indices, p and q, and these are numbers between 1 and n, and I specifically want p to be less than q, strictly less than q. And I also want the property that the set has is that the pth term on this list is bigger than the qth term. Okay, so remember that p is less than q, and so saying that the pth term is bigger than the qth term is saying that those two numbers are out of order. So I have a bigger number appearing before a smaller number. And really what I care about, instead of this set itself, is I just care about the size of this set. This set S actually has a name. So when you're looking at permutations, this set is the set of inversions of the permutation. So it's the number of pairs of numbers which are out of order. So now we can take -1 to the power of the number of inversions, and that is how we get the sign of the term itself. So this term has a plus or minus sign in it. How do we know what that sign is? Well, we make this list, we figure out the size of this set, and we do -1 to the power of the size of that set. Now, in general, this is going to be a fairly difficult thing to get a handle on, but the only reason I'm saying this is because we only care about one sign. That one sign that we care about is going to correspond to all of these numbers being exactly in order. So J1 is 1, J2 is 2, and Jn is n. All of them are exactly in order. What does that mean? Well, that means that J sub I is always equal to I, which means this is B11, this is B22, all the way up through Bnn. In other words, we just have the product of the diagonal elements of our matrix. And if we are looking at this list here, 1, 2, 3, 4, all the way up through n, and we want to count the number of things that are out of order, there's nothing there. So the set S for that particular term is going to be empty. And so the size of S is going to be 0, and -1 to the 0 is going to be +1. Okay? So there's going to be a plus sign that shows up specifically in the term where we have just the diagonal elements. So the term with only diagonal entries has a positive sign. Every other term will have a factor bij with I not equal to j. The only term that has all factors where the I and the j's are equal is this one right here. That's the one made up of only diagonal factors. So every other term has some off-diagonal factor, and since each row I and each column j can only appear in one of the factors, having something that's off of the diagonal is going to eliminate the diagonal entry that's on that same row and eliminate a different diagonal entry that's on that same column. And so you're going to be missing two factors that are on the diagonal. So the term will necessarily not have the factor that looks like BII, nor will it have the factor that looks like BJJ. And these two are not the same factor because I is not equal to j when we're not looking at this term. So what that means is the only term in the determinant of this matrix, A minus xi, which actually has at least n minus 1 factors that have an x in them, is the term that has all of the factors. If you're missing any one of these factors, that's the same thing as having a factor that's in an off diagonal entry. So let's say, for example, if this factor was in your term, then you couldn't have this factor, nor could you have this factor, because this one's in the same column and this one's in the same row. Okay, which means at most, if you have this factor right here, you could have at most n minus 2 of the other diagonal factors, which means that term has a maximum, or the degree of that term as a polynomial in x is at most n minus 2. So what we're going to be looking at now is the coefficient of x to the n minus 1 in the characteristic polynomial. The coefficient will turn out to be the trace, as we'll show in a second. And the idea is that the terms that have degree at most n minus 2 will not be contributing to the coefficient here, so we don't care about them. And there's only one term that has degree that's at least n minus 1, and it's this term, which has degree n. And we're only going to look at that term. So the coefficient of x to the n minus 1 in the characteristic polynomial is exactly the same as the coefficient of x to the n minus 1 in this one term, because that one term is the only one contributing to the coefficient. So now we can expand out this term here to see exactly what the coefficient of x to the n minus 1 is. So this is the term here, and we want to start by multiplying one of these two by one of these two by one of these two to, well, we're going to start out by getting as many x's as possible. The way to get the most number of x's is to, in each one of these parentheses where you have a choice between the number and the x, we're going to choose the x. So if we choose that x, all the way up through that x, then we have n of those x's. And then we also have to worry about there's a sign in front of this, which is -1 to the n, because there's n negative signs coming from each of those choices of x. So now if we want to make sure to get exactly n minus 1 x's, then when we're going through these parentheses and making a choice between the constant and the x each time, we want all but one of our choices to be the x. So we're going to choose one of these to be the number, and the rest of the choices are going to be the x. So here I'm going to choose the number a11, and then multiply it by this x, and the next x, and the next x, etc. So that's going to contribute a11 times x to the n minus 1, and then each of the x's have a negative sign on them, so I also have a factor of -1 raised to the same n minus 1. Okay? Another way to get an x to the n minus 1, when you expand this out, is to choose the negative x here, and then choose the number here, and then choose the rest to be x's. So that's going to give us a22 times x to the n minus 1, and again, each of those x's has a -1 attached to them, so we have -1 to the n minus 1. Okay? And we can choose each of these numbers individually when we're making these choices in the expansion, and when we do that, we just get the sum of all those numbers. So the sum of the diagonal entries is right here. This is exactly the trace of A. Okay? How do we know that's equal to the sum of the eigenvalues? Well, we can list out the eigenvalues. An n by n matrix will always have n eigenvalues. These are not necessarily distinct, nor are they necessarily real, but they always exist. So once we have these, we can do the exact same thing. We know these are all roots of the polynomial, so we can write this like this. Okay? Whenever you have all the roots of the polynomial listed, you can always do something like this. Usually you have to worry about maybe multiplying by some constant out in front, but it turns out in this case this constant will be 1, and I'll explain why in a second. So what happens when we take this and multiply it out? Well, the exact same thing is going to happen because it's in the exact same format. So we're going to get -1 to the n times x to the n plus this. And right here, you can see we have the sum of the eigenvalues. Okay, so how do we know that the number out in front was correct? Well, we need to note that this argument that we had for the coefficient of x to the n minus 1 in the determinant is the same as the coefficient of x to the n minus 1 in this term, because every other term had at most degree n minus 2. Well, that also says that the coefficient of x to the n is the same in both of these things. So the coefficient of x to the n is the same in the characteristic polynomial as it is in this one term right here. And notice that the coefficient of x to the n is negative 1 to the n in both of these terms. Therefore, I had the number out in front. The constant that I might have to multiply by is just 1. So these two are actually going to be, they're not equal, but they have the exact same first two coefficients. So that proves this theorem right here. We just said that the coefficient of x to the n minus 1 here has to match the coefficient of x to the n minus 1 there, and the sum of the eigenvalues has to equal the trace. Okay. Notice that it isn't exactly necessarily the trace depending on the value of n. There might be a minus sign, but if there's a minus sign in one of these, then there's also a minus sign in the other, so you can just think about it not being there. Factor it out. Okay, so I want to now make this a two-part theorem. So if A is an n by n matrix, then this first part we just proved. And now I want to say the determinant of the matrix A is the product of the eigenvalues. Okay, how might we go about showing this? Well, we're actually almost done with showing this. Notice that we have the eigenvalues listed right here at lambda 1 through lambda n, and their product is sitting right here. It's the constant term of this characteristic polynomial. Well, another way to express the constant term of any polynomial is to evaluate that polynomial at x equals 0. So the constant term lambda 1 times lambda 2 all the way up through lambda n should be equal to the determinant of a minus 0i. Okay, well, a minus 0i is just the matrix A. So the product of the eigenvalues, the constant term in the characteristic polynomial, is always just the determinant of the matrix. All right, thank you for watching.